All right, I'm going to begin section 5.2, which is called inverse functions. There's a definition that says if f is a function, then the inverse of f receives as input a number, which we'll call f of x. It manipulates it and then outputs the value x. So that is exactly the opposite of what the original function does. We know the original function receives as input the x values and then outputs the f of x values. So here we've got that switched. Whenever you are calculating an inverse, it's all about switching x and y. That's the first thing that I want you to think of when you see the word inverse, is that you're just going to simply switch x and y. Okay. So here's some examples. I want us to find the inverse. Note that we do have a function in this problem here. So each person has exactly one birthday. The fact that Andy and Nate share the same birthday, that's fine. We still have a function because each person has exactly one birthday. Nobody can have two different birthdays, otherwise it wouldn't be a function in that situation. That's also impossible, of course, for somebody to have two different birthdays. Now, if I want to find the inverse of this function here, it's all about switching x and y. So all I would do is I would just simply switch the two sides on the diagram, and so the birthdays would be my input, and the names would be the output here. Okay, and so this picture here would be my answer. That would be the inverse of the function that was given. Here's another example. I've got a set of points. This is a function. Again, each x value is going to only one y value in this set of points. If I want to calculate the inverse, it would also be a set of points. And again, all we're doing is just switching x and y. So all I would do here is just simply switch the coordinates on the points that were given to get this new set of points. This new set of points would be my answer. That would be the inverse of the function that was given. Now, sometimes when we calculate an inverse, the inverse of a function is not a function, and sometimes it is a function. It just depends. There's a definition: if the inverse of a function f is also a function, then the original function f is called one-to-one. Okay, so if I go back to my first example, here's my function, and here's the inverse. Now, this function is not one-to-one because when we calculate the inverse turns out not to be a function. You have an x value going to two different y values. You can't have that with functions. So this function is not one-to-one, we would say. In this other example, I had a function. Here's the inverse. Now this function is one-to-one because when you calculate the inverse turns out also to be a function. Okay? So one-to-one just simply means that the inverse is also a function. We talked about the vertical line test back when we first started talking about functions. We also have something that's called the horizontal line test, and it says if every horizontal line intersects the graph of a function f and at most one point, then the original function f is one-to-one. So here's two examples. The first example, I have the square function, and of course that's a parabola centered at the origin facing up. I've left the scaling off. It's not important for what we're doing here at the moment. But notice that this function would not be one-to-one since it would fail the horizontal line test. If you swing a horizontal line down the graph, it would intersect at more than one point. Now what that means to us is that this function has an inverse, and whatever curve that looks like, it would be some curve that would fail the vertical line test. The inverse is not a function. Here's another example. Using the cube function, and notice how this would pass the horizontal line test. Okay, so this function is one-to-one because it passes that test. Now what that means to us is that this function has an inverse, and whatever curve that looks like, it would be some curve that would pass the vertical line test. Okay, the inverse is a function. Here's the next thing that we'd like to know is the inverse function notation. When you see this symbol, the way that we'd read that is f inverse of x. You want to be careful because the -1 is not a power of f. Okay, So you don't want to think of this as f of x to the negative 1 power. F of x to the negative 1 power would be the same as 1 over f of x. But again, negative 1 is not a power, so these two things would not be equal. Okay? The negative 1 is just strictly a symbol to represent the word inverse. Okay? Now, you only want to be using this inverse function notation if f is 1 to 1. Okay? If f is not 1 to 1, we wouldn't want to be doing anything with function notation if the inverse is not a function. All right, so you want to be careful about that. Sometimes it would be appropriate to use this notation, and sometimes it would not be. Of course, you only want to use the inverse function notation when you have a function that is 1 to 1. All right, let f be 1 to 1, so that means that the inverse is a function. Then g is the inverse function of f if f composed g of x is x and g composed f of x is also x. The way to check if two functions are inverses of each other is through function composition. You got to make sure that you get plain old x on each one of those. So here's an example. I want us to verify that the inverse of f of x equal 2x plus 3 is f inverse of x equal 1/2 the quantity times x minus 3. Well, to verify that, I'm going to plug each function into the other and check and see that I get plain old x. So I'm doing that here. If I plug the inverse function into f, then everywhere that I see an x in f, there's only one, I'm going to replace that with 1/2 the quantity x minus 3. So I've done that, and when you distribute the 2 times 1/2 is 1. X minus 3 plus 3, the 3 is negative 3 plus 3 is 0, and so that'll leave you with just x. You also want to check that f inverse of f of x is x. So now f of x is 2x plus 3, which means that everywhere in the inverse function where we see x, there's only one, we need to replace that with 2x plus 3. And so I've done that. 2x plus 3 minus 3, the 3 minus 3 is 0. 1/2 times 2x would be x, since the 2's would cancel there. So since both of these items resulted in just x, that would tell us that indeed these two functions are inverses of each other. And the way to check in general would be to plug each function into the other and check that you get plain old x. For the last few problems, I want us to find the inverse of the function, the domain of the function, and the range of the function. So here's an example. I've got a graph of a function. That's what's drawn in pencil here. I'm calling that f of x, and I've got some points labeled. Now, if I want to find the inverse of f, it's all about switching x and y. So with these points, I would just simply switch the coordinates and plot the new points. Negative 2, negative 1 would now be at negative 1, negative 2. Negative 1, 0 would now be at 0, negative 1. 2, 1 would now be at 1, 2. And so this curve that I drew in red would be the inverse of f. Now, notice that f is 1 to 1. I can know that right away because f passes the horizontal line test. I could also know that from what I've calculated here with the inverse. The inverse is a function, right? This curve here in red passes the vertical line test. So f was 1 to 1. Which means that if I wanted to use the inverse function notation, like it would be okay for me to do that here. I've also drawn the line y equal x because in general, when you graph a function and its inverse on the same picture, they will always be symmetric to the line y equal x. That will always happen. So one way to think of how I got the curve in red is I started with the curve that was in pencil, and I rotated that curve about the diagonal line y equal x. All the points would land in the spots that you see here, that is the curve in red. Now let's also state the domain and the range of f. Here's f of x. The domain is all the x values. Notice how we are going from negative 2 to 2 on the x-axis. We're including those endpoints, and if you look above or below, you're going to be on that curve that was in pencil there. To get the range of f, I got a couple of options. The way that we are familiar with is to scan the y-axis and look to the left and to the right, and if you're on the graph, you're in the range. Okay, so again, I'm talking about the one that I've drawn here in pencil. If I am between 1 and negative 1 on the y-axis, and I look to the left or the right, I'm going to be on that graph that was drawn in pencil. So the set of all y is such that y is between -1 and 1, including the endpoints. That would be the range of f. Now, the range of a function is always the same as the domain of the inverse. So another option that I could have used is I could have looked at the inverse and stated its domain. The inverse is in red. Domain means we're talking about x. Now notice how x is ranging from -1 to 1 for the curve in red. That would be the exact same set of numbers that I've stated here from scanning the y-axis. Okay, that will always happen, and that's a handy thing to know when it comes to calculating an inverse. If they ask us to find a range of a function, sometimes it's quicker just to calculate the inverse and state the domain of the inverse. We'll see that later. Here's another example. So I've got the function f of x equal 2x plus 3. I don't have a graph, that's okay. I still want to calculate the inverse. So y and f of x mean the same thing, which means that I've rewritten this equation in terms of y and x. There's no harm with doing that. Now, since I want to calculate an inverse, again, it's all about switching x and y. So I switch x and y, and now I would have to solve this equation here for y to get the inverse. If I subtract 3 and then divide by 2, y would be equal to 1/2 the quantity x minus 3. And if I wanted to use the inverse function notation, that would be okay. I could call this f inverse of x, which is equal to 1/2 the quantity x minus 3. Now, in order to know that that is correct, we've already verified this from an earlier problem. Here's f of x equal 2x plus 3, and that's the same function that I just gave you here. Now, in this problem from earlier, I just told you the inverse. I didn't say where it was coming or anything like that, but we now know where that is coming from. Here's how you would calculate that inverse, and I guess this would be a rare time where we have checked our answer before we have computed the answer type thing. So I know that this is correct, which means I can go ahead and circle the result. I've already checked that from this example up here. We also want to find the domain and the range of f. F is a linear function. The domain of any linear function is all real numbers. The range of any linear function would also be all real numbers, as long as it's not a horizontal line, which I don't have a horizontal line. This would be a slanted line for this problem. I could have also stated the domain of the inverse. See, the f inverse is also a line. Y equal 1/2 x minus 3/2, that would be a line. And so its domain would also be all real numbers. Okay, the range of a function is the same as the domain of the inverse. So in this case, that'd be all real numbers. I got 2 more examples here. So my next one, here's f of x equal negative x squared plus 2. I want to calculate the inverse. So I'm going to first rewrite this in terms of y. Y and f of x mean the same thing. And then the next thing is you're going to switch x and y, and then solve this equation here for y. Well, if I subtract 2 and then multiply by -1, and then take the square root of both sides, don't forget about the plus or minus, then y is equal to plus or minus the square root of 2 minus x. Now, that would be my answer. That's the inverse. F is not 1 to 1. Remember, 1 to 1 just means that the inverse is a function, and the inverse is not a function. Okay? We know that for a function, for each x, there's only one y. There's not a plus y and a minus y. There's only one y. So in this problem here, I wouldn't want to use the inverse function notation. I wouldn't want to call this f inverse of x. If I did that, it's like I missed the idea of the concept of a function, because I don't have a function. So you want to be careful about using the inverse function notation, like I said earlier. Sometimes it's appropriate to use it, and sometimes it's not. It's not appropriate to use inverse function notation for this problem here. So you would just leave the answer in terms of y and x. F is not 1 to 1, so there is no inverse function. Now, I want to be careful about how I word that. I'm not saying that there's no inverse. Every function has an inverse. We just computed it right here. I'm just simply saying that the inverse is not a function, right? Every function has an inverse, but whether the inverse is a function, that's another question. So again, we don't have a function going on with the inverse, so that's why we don't want to be using the inverse function notation. Okay, suppose that we also wanted to know the domain and the range of f. F is a quadratic function. We did lots of things with quadratic functions in Chapter 3. The domain of any quadratic function is all real numbers. A quadratic function is a parabola, right? So this parabola would be flipped upside down and then shifted up 2 units. So the range would be anything that is 2 or less on the y-axis. Okay, since the vertex of this parabola would be at 0, 2. That's one way that you could get this. Another option is you could state the domain of the inverse. So I've calculated the inverse. Of course, I know that 2 minus x can't be a negative. So if I were to do like a side calculation here, set 2 minus x to be non-negative, and solve for x, it looks like anything less than or equal to 2 would be okay to use. Anything bigger than 2, we don't want that because now we got a negative underneath the square root sign there. Of course, I'd want to give my answer in terms of y, not x, since I'm talking about the range of f. Okay, but it's the same set of numbers that you're describing there. My last example, okay, here's f of x equal 1 over x plus 2. I want to calculate the inverse. First rewrite this in terms of y and x, and then switch x and y, and then solve for y. If you multiply both sides by y plus 2, and then distribute x there, subtract 2x, and then divide by x. That'll make y all alone. And so y would be equal to 1 minus 2x all over x. Now I didn't have any plus minus deal come up like I did in the last problem, so here would be another situation where it would be okay for me to use the inverse function notation since the inverse is a function. If I wanted to check that the inverse is correct, I can check that through function composition. So I got to plug each function into the other and check that I get plain old x. Here's the calculation for doing that. So I'm going to first plug what I think is the inverse into f. Everywhere that I see an x and f, there's only 1. Replace that with 1 minus 2x over x. Okay, now does this simplify to be just x? That's the next question. 2 is the same as 2 over 1. So you'd want to multiply the top and bottom by x. That way you get your common denominator of x. So you can add these fractions here. You've got your common denominator, add the numerators. 1 minus 2x plus 2x, negative 2x plus 2x is 0. And then 1 divided by 1 over x. You'd flip the denominator, and that would give you just x. I also want to check that f inverse of f of x is just x. Now f of x is 1 over x plus 2, so everywhere that I see an x in the inverse function here, there's 2 of them, I need to replace that with 1 over x plus 2. And so I've done that. The next question then, does this simplify to be just x? So up top, 1 is the same as x plus 2 over x plus 2, and that's how I'd want to think of that because now I've got my common denominator up top. And so I can add the numerators. X plus 2 minus 2. The 2's cancel there, and that would leave you with x over x plus 2 divided by 1 over x plus 2. Now, since you're dividing by a fraction, the next thing would be to flip the denominator. The x plus 2's would then cancel, leaving you with x over 1, or just x. Okay, so these calculations here, checking out to be just x, tell me that indeed I've got the right answer computed, representing the inverse. We also want to state the domain and the range of f. Here's f of x. I can't use negative 2. That'd be a problem because I know I can't divide by 0. So set of all x such that x is not equal to negative 2. Now if I wanted to know the range of f, I think the easiest thing to do there would be to state the domain of the inverse. Here's the inverse. I know I can't divide by 0, so just don't let x be 0. And of course I want to state the range in terms of y. It'd be the set of all y such that y is not equal to 0. Okay. Another way to look at it too is that you've got a rational function. There would be a horizontal asymptote at y equals 0. We talked about that in the last chapter. And so one reason why we're throwing away 0 is because the curve is going to be approaching the x-axis, or y equals 0, but it's never going to get there because there's an asymptote on that, or there's a boundary there at that spot. Okay, that's it for section 5.2. Here's the problems on page 415 that you'll want to look at when you get a chance.